Okay, in this video we will discuss about the formation of Laplace and inverse Laplace transforms from power series expansion of a function. Since Laplace transforms is a tool for solving differential equations, we will consider a differential equation y dash equal to cy, or we'll assume it is dy by dt equal to cy. Okay, now the power series solution of this equation may be assumed as sigma n equal to 0 to infinity a n t to the power n. Then dy by dt will be summation n is equal to 1 to infinity a n t to the power n minus 1. So if you apply a shifting procedure, inside we will get a n plus 1 n plus 1 t to the power n by shifting one unit forward, and applying a backward shift here in the summation, sigma varies from n equal to 0 to infinity a n plus 1 n plus 1 duration. So we will substitute for dy by dt from here, and then for y from here. That will imply a relation for a n plus 1 as equal to c multiplied by a n divided by n plus 1, or n equal to 0, 1, 2, etc. Now this implies that a n is equal to c raised to n a naught divided by n factor. Okay, so we substitute that here and we'll obtain the solution as summation equal to 0 to infinity c raised to n a naught t raised to n divided by n factor, which is equal to a naught multiplied by e to the power c. So thus we have the solution of this differential equation as yt equal to y of 0 e to the power c, where a naught is equal to y of 0. Because you substitute 0 here, then y of 0 will be the only term that will not vanish on the RHS is a naught. So y of 0 is equal to a naught. Now this power series expansion of the solution yt, that has some connection with the derivatives of y. We know that relation is summation equal to 0 to infinity yn 0. So this is the nth derivative of y evaluated at 0 divided by n factorial t to the power n. Okay, now we will consider an integral that is a bit different from this topic, which is a complex integral of the form 1 by 2 pi I, where I is the imaginary square root of minus 1, gamma minus I infinity, gamma plus I infinity, e to the power s t ds divided by s to the power n plus 1. So this is the integral that we will consider. Now if we apply Cauchy's residue theorem, we will obtain this integral as 2 pi I multiplied by residue at 0, because here the integrand is e to the power st divided by s raised to n plus 1, which is not analytic at the point s equal to 0, but the denominator vanishes, and therefore it is a pole, and hence this integral is 2 pi multiplied by residue at 0. Now this is 2 pi gets cancelled, and residue at 0 is the coefficient of 1 by s in the expansion of power series expansion of e to the power st divided by s to the power n plus 1. So e to the power st we know is summation I equal to 0 to infinity st to the power I divided by I factorial divided by s to the power n plus 1. So when we expand this summation over the index I, there is a term. So it involves several terms plus a term s raised to n e raised to n divided by n factorial whole divided by s to the power n plus 1. So when we simplify it, it has the form 1 by s multiplied by t raised to n by n factorial. Okay, s raised to n gets cancelled and we have. So therefore, the coefficient of 1 by s in the expansion of e to the power st by s to the power n plus 1 is nothing but t raised to n by n factorial. And hence, we can conclude that this integral is t raised to n divided by n factorial. And therefore, we can substitute for this t raised to n by n factorial that appears here, and we can write yn0 divided by n fact. Okay, we are taking that together. So 1 by 2 pi I integral gamma minus I infinity to gamma plus I infinity e to the power st divided by s to the power n plus 1 dx. Okay. Now we will talk about another integral, which is integral 0 to infinity u to the power n e to the power minus st dt du e to the power minus su d. Now some algebra shows that, or by opting integration by parts, we can see that this is equal to n factorial divided by s to the power n plus 1. Okay. For example, when n is equal to 0, we have 1 here and the answer is 1 by s. So for 1 by s to the power n plus 1, we can substitute from here as 1 by n factorial u raised to n e raised to minus su d. Okay, so that is what we are going to do next. 1 by n s raised to n plus 1 that appears here, we will substitute for 1 by s raised to n plus 1 as 1 by n factorial integral 0 to infinity u to the power n e to the power minus su du. And earlier there was an e to the power st and d's was there. So that is also written here. Now what we will do is, we will take this summation here inside this integral. So that becomes 1 by 2 pi I integral gamma minus I infinity to gamma plus I infinity. Again integral 0 to infinity summation n equal to 0 to infinity yn 0 divided by n factorial u to the power n. So this we will put in a bracket e raised to minus su here du, that again in a bracket multiplied by e to the power st ds. Okay. Now we see that this summation that appears here is nothing but y of u. See, from here you can observe that instead of t, here it is u. So this is nothing but this summation can be replaced by y of u. So what do we have? We started from here y of t and we ended up at here. So this is a representation of y of t. So we will write that representation here. Y of t equal to 1 by 2 pi I integral gamma minus I infinity to gamma plus I infinity integral 0 to infinity y of u e to the power minus su du multiplied by e to the power st ds. So that is the representation for yt. Okay. Now similarly, one can have the representation of y dash t, which is dy by dt, as 1 by 2 pi I integral gamma minus I infinity ds. Okay. Now here we will apply integration by parts and we will obtain integral of y dash u is y of u e to the power minus su over the limit 0 to infinity minus integral y of u e to the power minus su multiplied by minus s du 0 to infinity whole multiplied by e to the power st ds is ds. Okay. Now this we can see that it when we apply the upper limit it is 0 and when we apply the lower limit it is y of 0, and therefore this integral that can be replaced as integral 0 to infinity y of u raised to minus su, this term, but there is an s here, so s multiplied by this term. Okay, this term comes here, then minus y of 0 that multiplied by e to the power st ds. Okay, so this is what we will obtain for y dash. Now we will substitute that here in the differential equation y dash equal to cy. So we have to multiply this with the c, so we'll do that. We will multiply this with the c, and y dash t equal to c times yt. That comparison gives, assuming some uniqueness here, we can compare these two terms and say that these two are equal. So we will write that 0 to infinity y of u e to the power minus su du equal minus y of 0, this term is equal to c times integral 0 to infinity y of u raised to minus su du. Now we can take this term to the LHS so that we will have s minus c here. We can answer this, and we can take minus y of 0 to RHS, so that equation becomes equal to y of 0. Or we will obtain integral 0 to infinity y of u raised to minus s will be as s minus y of 0 by s minus. Okay, so this guy. So here is the representation of yt that we obtained earlier. Now this integral that appears here, we have seen that it is equal to y of 0 by s minus. So we can substitute here for this integral as y of 0 divided by s minus c. Now again we have a complex integral, so that is equal to 1 by 2 pi I by applying Cauchy's residue theorem. This 2 pi I multiplied by residue at c. So here the integrand is not analytic at s equal to c, so you have to multiply with the residue at c, and that is equal to 2 pi I gets cancelled, y naught e to the power ct is the residue. So we started from here and we obtained the solution that we obtained earlier using the power series expansion yt equal to y of 0 e to the power ct, and hence what we have seen is that we have got a representation of yt as integral 0 to infinity y of u e to the power minus su d. Okay, now this integral that appears here is called the Laplace transform of the function y. So L of y is defined as integral 0 to infinity yu e to the power minus su du. We can very well use the variable t here. That is, we will define L of y as integral 0 to infinity yt e to the power minus st dt. The reason why we didn't do that here is because we have already used a t here. So that is why we used the variable u. So if we define this as the Laplace transform, this integral as the Laplace transform, then we find out that Laplace transform of y dash is s times Laplace transform of y minus y of 0, and we apply that here in the differential equation, and we obtain L of y as y of 0 divided by s minus c. Now that we substitute that here and obtain y of t as y naught e to the power ct. Now this procedure of obtaining y from the Laplace transform is called inverse Laplace transform. Okay, so we have L of y equal to this, and therefore y is equal to L inverse of y of 0 divided by s minus c. So that is what we are doing here. Using this integration, we are actually inverting the Laplace transform. Okay, so we have the Laplace transform in this equation, and we invert that to obtain the solution of the differential equation. So this is how we use the Laplace transform and its inverse Laplace transform for solving a differential equation. So the Laplace transform of a function is defined as this integral, and its inverse Laplace transform is defined by the complex integral that appears in the outer.